Welcome to this lecture series in real analysis. In this lecture, we'll look at the nested interval property, and as a consequence, we will be able to nail down the cardinality of the set of real numbers. So let us recall what we need. We will need the notion of compactness. So a subset A of R is said to be compact if every open cover of A admits a finite subcover, and we showed that compact sets are precisely the closed and bounded sets. We will use the fact that the rationals are dense in R. We will also use the fact that the cardinality of this set, which is the set of all maps from a set X to 0, 1, is same as the cardinality of the power set. So there is a natural bijection between this and that is what leads to this. And we will also make use of this Cantor-Schroeder-Bernstein theorem, which says that if we have an injection from a set A to a set B, and we have an injection from a set B from the set B to set A, then there is a bijection between A and B. I don't know how to write a bijection, but anyway, so that's the theorem, and that is what we will use at one point. So let's proceed. Here are some problems for practice. And now let us get started. So first we will prove this finite intersection property. So suppose we have a sequence of compact subsets of R. So A1, A2, A3, ... are all compact subsets of R. Assume that whenever we pick a finite subset of natural numbers, we find that the corresponding ANs, meaning the AN where n is varying over F, their intersection is non-empty. There is always something in common whenever we intersect finitely many of these. Then magically it so happens that the intersection of all of them is also non-empty. So this is called the finite intersection property because of this hypothesis. Alright, so I hope the problem statement or the theorem statement is clear, and let us prove it. So suppose not, and say this is indeed empty, and we want to get a contradiction. Okay, now what is this thing? Well, clearly R is equal to this complement, because all we are doing is we are taking the complement of the empty set. This is the empty set, this is the complement of the empty set, and hence it is the entire set of real numbers. But this is also same as the union of complements of the individual things. Right? This is a purely set theoretic statement. What is this? This is those things which are not in all of them. Those real numbers which are not in each of AIs, which miss at least one AI. And what is this? This is those real numbers which miss AN. Now, since this is those real numbers which miss at least one AI, that's the same as this because we are taking union. So you can formally justify this, but this can be seen verbally. So we have that. And therefore, if we write script C to mean this set, or let's maybe give it a name. So let's give this a name. This is UN. And now if we define script C as the collection of all the UNs, this is an open cover of the reals. This is in fact, well, nothing to, this is exactly what I'm saying, that this is an open cover of R. Why? Because the union of the UNs is R, and each UN is open. Each UN is open because each AN is closed. AN is compact and hence in particular closed. Therefore, each UN is open, and the union of all the UNs is R, and therefore this statement is justified. But if it is an open cover of R, then it is in particular an open cover of A1 because A1 is a subset of R. And now by compactness of A1, there exist finitely many elements in C such that, give me a second, such that A1 is contained in the corresponding UNs. So this is an open cover of A1. A1 is compact, so there exists some finitely many things here whose union contains A1, and therefore we get finitely many natural numbers such that the corresponding UNs contain A1, which implies, by definition of the UNs, that this is contained in right? But again, we apply or we use this set theoretic fact that the union of the complements is complement of intersections, complement of the intersection. Right? This is what we used earlier. This equation and that equation are from the same principle. But then we would have A1 intersected with all these people. This is empty. Why? Because A1 is contained in the complement of these guys, so it is disjoint from them. And this contradicts the hypothesis that any finite subcollection of the AIs intersects in a non-empty set. We have contradicted that, and therefore our assumption that this is empty must be wrong, and that finishes this proof. So we have established this finite intersection property. Note that in the previous proof, the countability of our collection of compact sets was irrelevant. Any collection of compact sets which has the finite intersection property, meaning any finite subset of the indexing set, if any finite subset F of the indexing set has the property that the corresponding A alphas intersect in a non-empty set, then all the A alphas intersected gives a non-empty set. So here in the previous slide, J was the set of natural numbers. Here J is just some arbitrary set, that's all. And the same proof establishes this also. Okay. And immediate corollary of the previous page or this theorem is that if we have real numbers A1, A2, A3 and B1, B2, B3, such that the A1s, the AIs are increasing and BIs are decreasing, and AN is less than or equal to BN for each n, so the picture somewhat looks like this. We have A1, some A2, A3, and we have what I wanted to write was, so it automatically follows that. It follows that each BI is at least each AJ, right? Because this is a decreasing sequence, and this condition together imply that each BI dominates each AJ. Okay? All right. So the picture looks like this. At some point, these AIs get exhausted, and here we have B1, B2, B3. Maybe I should put dots like that. And what we are doing is we are intersecting all these closed intervals. So A1 up to B1, A2 up to B2, A3 up to B3, and so on. And this intersection will be non-empty. Why? Because if we define AN as this interval, then AN is compact, and A1, A2, A3, and so on, they have the finite intersection property, meaning if you pick any finite subcollection of the AIs, they intersect in a non-empty set, simply because of this nestedness. The first one contains the second one, contains the third one, and so on. So it has the finite intersection property, and therefore the intersection of all of them must also be non-empty. So this is a very nice consequence of what we just discovered. All right, and this is what we will refer to as nested interval property, which is a consequence of the finite intersection property or the finite intersection theorem. Okay. Now, the compactness in this, the hypothesis of compactness in the theorem about finite intersection property is essential, because if we drop it, we may define an as this open interval for each natural number n. Then, of course, the ans have finite intersection property. If you intersect any finite subcollection of them, you get a non-empty set. But if you intersect all of them, you get the empty set. Right? So just make sure you follow that. The intersection of all the ans is the empty set. So the compactness hypothesis was used essentially. All right. And now we will talk about what is called the Cantor set. A more proper discussion of this happens in a course on general topology, but we can appreciate what this is in fair amount of detail. So let X be this set. So the set is, this notation is just the same as all maps from, this is all maps from n to 0, 1. Or you can also think of it as all sequences. All 0, 1 sequences. Which means what? Which means all those sequences, ANs, where each AN is either 0 or 1. So this notation just means that, or you can also think of it that way. So this is a set, and there is one way to visualize it. Start with a node, just call it a root or whatever. And if you go left, you record a 0. If you go right, you record a 1. So 0, 1, 0, 0, and so on. And you just keep on going. It's not a finite thing. It just keeps on developing. So every 0, 1 sequence gives rise to an infinite path in this infinite tree. And every infinite path in this infinite tree gives rise to a 0, 1 sequence. So every point of X can be thought of as an infinite path in this grisly object. Okay, now what are we going to do is, we are going to associate to each element of X a real number. How? For this pink, the root, just consider this interval 0, 1. So this interval has endpoints 0 and 1. Okay. To this, associate this interval, which is the left third of the previous one. So the left third of the previous one would be the interval 0, 1 by 3, closed interval. And to this blue dot, associate in your mind, by when I say associate, just associate in your mind this guy, and this is the right third of the previous one. So its endpoints are 2 by 3 and 1. All right, wonderful. And similarly, just keep on iterating. To this guy, associate to this guy, associate that one, which is the left third of the previous one. So the left third of the previous one has endpoints 0 and 1 by 9. And to this guy, associate this guy, which is the right third of the previous one, which has endpoints God knows what. So the right endpoint is 1 by 3, and this will be 1 by 3 minus 1 by 9, which is, I think, 2 by 9. Yeah, and so on. So every blue dot here is associated with a closed interval. As you descend down on this tree, the length of the interval that is associated to any dot here is decreasing exponentially. So the length of the interval here is the length of the interval associated to this point is 1 by 3, to this point is 1 by 9, to this point is 1 by 27, and so on. So it will go on that way. And what is our function? So now suppose we have chosen some sequence, 0, 1 sequence, call it an. And just give me 1 second. What are we associating? What is the image of this guy under the map F? So first we get a path here. Once we get a 0, 1 sequence, it gives us a path, some infinite path. And once we have an infinite path, by this association we get a nested sequence of closed intervals of decreasing length. In fact, the length is decreasing exponentially. So just intersect all the intervals that this path furnishes. So this path gives us this interval, and then maybe that one, and then that one, and maybe that one, and that. And this way, the intersection of all of these intervals that you get will be non-empty simply because it is a nested sequence of closed intervals, as we saw in the previous slide. That's a non-empty set, but at the same time, it is going to be a singleton. The intersection of all of them, as you take an infinite sequence, that will be just a singleton. It cannot have two different elements because the lengths of these intervals is going down to 0. Okay, so that part I don't want to formally justify. You can easily do it yourself. So the point, that is the image of this function. I don't know how to write it, so I've said it in words. What is the image of any point in X? Now, the crucial observation that I want to make is that, note that F is injective. Why? Because suppose we have two different points in X. So, two different infinite paths have been chosen. There will be a first time when they diverge. So, for instance, suppose we have this path and we have this path. So the first time they diverge is at this level, and the corresponding intervals that we get would be this one, then the left guy, then the right one, and then for the first path we will be choosing, okay, I'll draw it again. So this interval, that interval, well, the paths have disappeared. So the first path is this, and the second path is that. So for the first path, we will be choosing this interval, then the left one, then the right one, and then the left one, and then something here at the bottom. But for the second path, which is shown in dotted, we would be choosing this one. And therefore, the intersection of the first thing and the intersection of the second thing, they cannot be the same, because one of the, the point of intersection corresponding to the first choice will live somewhere here, while for the second choice will live somewhere here, and these are disjoint closed intervals. So therefore F is injective. Again, I'm not trying to write down a formal proof, but I hope you can fill the details if you really want to. So F is injective, and now finally this shows that the cardinality of R, all of this discussion shows that cardinality of R is at least, or let me write it this way, the cardinality of X is at most the cardinality of R, which means that there is an injection from X to R. But what is cardinality of X? The cardinality of X is the cardinality of this thing, which is same as the power set of natural numbers. So in particular, the real numbers are uncountable because this is uncountable. Okay. So that's the conclusion from the previous proposition, previous slide. But we can say more. To say more, first we will prove some preparatory material. So suppose we have three non-empty sets, x, y, z. Then we want to say that the cardinality of this set is same as the cardinality of that set. So this is just a purely set theoretic exercise. I think I must have done this in our primer on functions, but let me at least try to give some details. If not all the details, at least some details. So it's very simple actually. For a function of this sort and little x in capital X, define this as a function from y to z, which does what? Naturally, it takes y to that. So as soon as we are given a function here, meaning f is an element here, we can create an element. Okay, hold that thought. So as of now, for a function of this sort and an element of x, we have just defined a function from y to z. And now define capital phi from this set to that set as f going to which function? The function which takes little x to fx blank. Right? So what does phi do? Phi takes a function from x cross y to z to the function from x to that, which does what? Which picks little x from here and outputs this guy. So it may seem trippy, so many maps, but just think about it. It's not anything complicated. And similarly, we will construct a map in the reverse direction. So define, maybe I'll write it in somewhat non-conventional way. So we will define a map from this set to that set. So it is also the natural definition. You are given something, let's call it maybe, what's a good symbol? Let's say G. Not a great symbol, but anyway. So it takes G to what? G to the map which takes x comma y to gx of y. So you pick a map G which takes an element of x to a map from y to z. We map G to a map from x cross y to z which consumes an ordered pair. So little x is from here, little y is from there, and outputs an element of z. How? First you get gx. Gx is a function from y to z. Right? Gx is a function from y to z. So if you feed y to it, you get an element of z. So this is a well-defined map, and I leave you to check that psi composed phi is the identity map on this thing, and phi composed psi is the identity map on the other thing. And that establishes a bijection between this set and that set, and hence these two have the same cardinality. Okay. Preparatory lemma 2 is that the cardinality of this, meaning all rational sequences, is same as the power set of n. Okay, why is that? So I've written down a proof, let me just read it out. We start with the power set of n, or the cardinality of it. It is same as the cardinality of that set because there is a natural bijection between this set and the power set of n. But now since now since this is contained in rationals, the cardinality of the previous thing is at most the cardinality of the next thing. Clearly this is a bigger set than that. Everything here is contained here. So we have a less than equal to sign. But this by definition is equal to that. Okay, and this is equal to, well, again, we have written the same thing, so nothing happening. But since Q is in bijection with N, the cardinality of this is same as the cardinality of that. And now, since this set is clearly bigger in cardinality than that, we have this less than equal to. And now we use the previous proposition, the previous preparatory lemma. We have maps from X to maps Y and Z. So just think of this as capital X. Alexa, stop. So just think of this as capital X, think of this as capital Y, and think of this as capital Z in the previous preparatory lemma. We get that this cardinality is same as that cardinality. And now since n cross n is in bijection with n, we get that this cardinality is equal to that, but that is the power set of n. So there is a sandwich. This is at most that, is at most that. So this sandwich proves this equality. All right, and now we can talk about what is exactly the cardinality of the real numbers. The cardinality of the real numbers is same as the power set of n. So why is that? So we already have seen this part. We have seen that this is at most that thing. This is because of our Cantor set discussion. For the reverse, let C be equal to all those sequences of rationals which converge. Right? So this is a complicated way of writing all convergent rational sequences. This is all rational sequences. We are picking those which are convergent. And from here, there is the natural map. So from C to R, there is a map which just takes, call this map capital L. So this map takes a sequence and outputs the limit of the sequence. And L is surjective. So why is L surjective? The density of rationals, Q is dense in R, implies this implies that L is surjective, which implies that the cardinality of C is at least the cardinality of R, but C is contained in the set of all rational sequences. So we have this, but by the previous preparatory lemma, the cardinality of all rational sequences is same as the power set of n. So we have this, but now you combine this and that and use the Cantor-Schroeder-Bernstein theorem to deduce this. So we have nailed down the cardinality of the set of all real numbers. And as a corollary, we get this. I leave this as an exercise. Once you use this, the fact that the cardinality of reals is this, you can easily prove that, because just think of R2 as maps from the two element set to R. With that, you can easily prove. Okay, so yeah, with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.